All right, so let's get started. Before we get started again, I posted an announcement for the final arrangement. Like what we said before, the final arrangement will be taken again on Grayscope. The only difference here is for the final, it will take place from 3 p.m. to 6 p.m. So that's the window coming from the undergraduate office. The final will likely be 3 hours, 8 problems. I believe I already posted. If I haven't, I'll post it today. My previous year's final exam. So since I'm a little bit behind, I'll use all the 3 lectures we have left, just catching up on the material. And later this week, I'll post a video, just basically me walking through the previous final exams on a recorded version, so you can see what's going through my mind when I'm creating those problems. So, any questions before we move on? And your TA will be hosting review sessions and Q&A sessions. We're collecting times and making room reservations. We'll have those information ready on the announcement page as soon as possible. Any other questions? Okay, sounds good. So let's get started. So today we'll be talking about crystal field theory. So this is the second topic we want to cover for the transition metal complexes. We'll be talking about crystal field theory, ligand field theory, and how to deduct the d-splitting, basically the break of degeneracy in the d-atomic orbitals when a metal center is coordinated onto different ligands. And then at the end, we'll be talking about magnetism, color, and then structures of transition metal complexes, or in general, application of what we learned about bonding in the transition metal complexes. So, as a quick review, what we're talking about when we're saying a transition metal complex, normally you have the transition metal center being more electron positive or a more cationic behavior. And these transition metal centers are always stabilized when bonded to different ligands. So in our last lecture, we talked about 2 different types of ligand that's available in transition metal complexes. On the left-hand side, these chlorides, say the way we justify it is if we imagine both of the electrons in that metal ligand bond went to the ligand, and you look at it, and this chloride will have a -1 formal charge, so that makes them X-type ligand, or we call them anionic ligand. And as a quick practice, if we look at the chromium hexachloride, what's the oxidation state of the chromium center? So this is quite straightforward. We have 6 X-type or anionic ligands. So the center chromium is going to have a +6 oxidation number. And these are covalent bonds. So these terms are more or less interconvertible with each other. On the right-hand side, we have a different type of ligand that's more or less, different type of chemical bond that's more or less specialized to transition metal complexes. So if we look at it, imagine both of the ligand, both of the electrons in that cobalt nitrogen bond go to the nitrogen. By NH3 is still a neutral molecule. So these are called L-type ligands or neutral ligands. And the type of chemical bonds formed between a metal center and an L-type ligand is called a dative bond. So if we look at if you were to ask to calculate the oxidation number of the cobalt center here, we have 6 neutral ligands surrounding it, not changing its oxidation state. This entire molecule has a +3 charge, so my center cobalt has a +3 oxidation number. So this is a quick review on what we talked about, how to identify covalent bond versus dative bond, or anionic ligand versus neutral ligand, and use those information to derive what's the oxidation state of the center atom. And likewise, with the oxidation state, you can easily derive the d electron count of the center atom. So that's a quick review, refresh your memory on what we talked about in transition metal complexes. So today we want to go a little bit deeper into the d atomic orbitals in these transition metal complexes. So the theory we're going to be used is called crystal field theory. So the very foundation of crystal field theory is based on the ionic description of metal-ligand bonding. Or typically, crystal field theory treats all transition metal complexes as a center metal cation that's perturbed by negatively charged ligands. I know it doesn't make any sense to you. So what it means here is, let's imagine you have Coulomb repulsion between the d electron counts of the transition metal and also the negatively charged ligand. So this repulsion between the d electron and the electrons in the ligand will cause a split in the d atomic orbitals. So normally when we draw the d atomic orbitals, we say, hey, we have 5 d atomic orbitals, they're degenerate in energy, we expect them to have the same electronic energy. But what the crystal field theory is dictating is, after you have ligands surrounding your transition metal center, then your d electrons will no longer be degenerated. The interaction between the metal center and the ligand will cause a split in the energy level of your d atomic orbitals. Or, in short, what the crystal field theory is saying, electrons in the d atomic orbital were likely to repel the negatively charged ligands and leading to higher energy d orbitals. Again, it's a theory, it's an approximation. It's not 100% correct, but it's very useful in chemical setups. So let's put it in drawing and see what exactly is the crystal field theory speaking. Before we move on to look at crystal field theory and the splitting of the d atomic orbitals, let's just spend some time and draw the d atomic orbitals together as a quick review. So that's the coordinate system I put. That's the x, y, and z coordinates. So for d atomic orbitals, the x squared over y squared will have structures like this. And then we need to shade it accordingly. The z squared, that's the donut-shaped one. And we shade it accordingly. And then the xy, I think I have this one incorrectly drawn. So the x squared minus y squared should be a line along the x and y axis. The xy will be in between the axis. The xz will be in between like this. And then the yz will be in between. Just as a sanity check, whenever you're drawing the d atomic orbitals, again, it's a d atomic orbital, it always has 2 angular nodes. So it's always nice if you can check how many angular nodes it has. So for example, the dyz, you can draw the angular node like that. The z squared, you can draw it like this. And then the dxy, you can also draw it like this. So it's like a sanity check. After you draw the d atomic orbitals, just check the angular node and see if you do have 2 angular nodes in your atomic orbitals. So now we have the atomic orbitals of these d atomic orbitals. Then after we put the ligand on there, remember what we're saying is the electrons in the ligand will repel electrons in the d atomic orbitals. and cause a split in energy for the atomic orbitals that used to be degenerate with each other. So now what we're doing is putting the ligand on, imagine we have ligand surrounding that transition metal center. So our metal center is like in here. So where are those ligands? We'll start from the most common orientation of the ligand, which is called octahedral. So the way we draw it, imagine we have the metal in the center, and in octahedral complexes, we have ligand that's 90 degrees to each other. Or if you put these ligands onto the axis, you can imagine two ligands on the x-axis, two on the z-axis, and two on the y-axis, surrounding that center metal center. So now, when we overlay our d-atomic orbitals with these ligands, this is what happens. We'll draw the atomic orbital again. The x squared minus y squared is directly pointing towards these ligands. So in these cases, the x squared minus y squared is directly overlaid with the 4 of the ligand. So it's directly pointing towards 4 of the ligands. So these, we expected to cause more interaction between that filled d-electron orbital and the ligand. Or in the other word to say, it's because your orbital is directly pointing towards the ligand, we're expecting larger electronic repulsion and higher energy in the dx squared minus y squared case. The dz squared is the same story, just less obvious. So in this case, that's the donut-shaped one. So in here, we have direct interaction between the two Z ligands and less direct interaction with all of the 4 ligands. So for the dz squared atomic orbitals, you have 2 direct interaction and 4 less direct interaction. But taken together, it also has a very large repulsion. All right, so that large repulsion coming from the d-atomic orbital pointing directly towards the ligand, causing more interaction and more destabilizing electron repulsion energy, and making these 2 atomic orbitals higher in energy. And in contrast, we have 2 that are suffering from higher electron repulsion energy. We have 3 of them that have smaller repulsion energy. So if we think about the xy, so the xy goes in between x-axis and y-axis. Right, so the xy atomic orbital doesn't directly interact with any of the ligands in the xy plane. It's like indirect overlap with the ligand in the xy plane. Or I can use this red color suggesting it's indirect pointing. And the 2 ligand on the z-axis is not interacting with the dxy at all. So these will have smaller repulsion. And relatively speaking, lower energy. The same applies to the xz and the yz. We'll just draw it here. The xz. So for the xz, it looks like my sketching is overlapping with y, but taking consideration y is actually going in and out of my xz plane, it doesn't. Those 2 ligands on the y plane does not interact with the d orbital at all. So we have 4 indirect overlap. It just because I'm drawing it this way doesn't mean the y ligand is in position to overlay. For the dyz, it's the same story. we have 4 indirect overlap. And those are just smaller overlap between the ligand and the diatomic orbitals, smaller repulsion. All right, so at this moment, by just drawing the atomic orbitals and placing the ligand surrounding that atomic orbital, what we can derive is we expect the x squared minus y squared and the z squared has higher energy. The xy, xz, and yz have lower energy. So when we put those information onto the energy splitting diagram, this is what we have. What we have at the beginning is without any ligand surrounding that transition metal center, we have the 5d atomic orbital degenerate in energy. Again, degenerate in energy means they have the same energy level. And then, imagine now you have a spherical ligand field surrounding it. It's hypothetical, it doesn't exist in real life. Spherical ligand field. And then this negatively spherical ligand field will raise up the energy level of your d orbitals because of the electron-electron repulsion. So now, in the hypothetical spherical ligand field, you just imagine a negatively charged spherical electric field surrounding that metal center. And then, like what we said, your different diatomic orbitals will interact differently with your actual ligand field, which is octahedral, and ends up to create a split in your d electrons. So dx squared minus y squared and dz squared will have higher energy, and dxy, dxz, and dyz will have lower energy. And in here, we can actually quantify this splitting. So this entire splitting is this little delta node. That's total splitting. And then for the dxy, dxz, and dyz, these will be 5/2 of the total. And on the top, we have 3/5. So those numbers, the splitting numbers, are a little bit extra. I only need you to know like which one of them are higher, which one of them are lower. I don't need to quantify those splitting energies. You'll learn that in inorganic chemistry. So that's the general pattern for an octahedral crystal splitting. And then we actually have 2 different scenarios describing that splitting pattern. So now, remember, we have different energy in these diatomic orbitals. So when we're putting electrons in there, say if we have 4 electrons, naturally we need to make a choice. Does that 4 electron go to the higher lying dx squared minus y squared, dz squared, or it pairs up? So what's the relative energy between the electron pairing energy and the difference between these splitted diatomic orbitals? So for that, we want to introduce the idea of high spin and low spin complexes. So before I move on to talk about high spin and low spin, do we have any questions? I'm just going to go back here and see if we have questions. All right, sounds good. So high spin and low spin complexes. So depending on the identity of your ligand, you can have high spin and low spin complexes, or in the other way, you can have weak field and strong field configuration. So let's just look at 2 different examples here. We'll use the water here. This is an example of a weak field ligand. So what it means is we're expecting it to have a small crystal splitting energy. So by say small crystal splitting, so the difference between dxy, xz, and dyz and the dx squared minus y squared, this is the crystal splitting. So by say it's a weak field, we have the crystal splitting smaller than electron pairing energy. And we call them weak fields configuration. Or this complex is called a high-spin complex. So in the manganese hexa water, let's just do the quick electron count. The manganese is 3+ in the middle because the water ligands are neutral. So manganese 3+. So in total, we have 4 d electrons. So this is a practice you should get familiar with, how to quickly translate a transition metal complex into the d electron count. So manganese 3, we have d4 electrons. So when we put the electron in, originally we have 4 of them in the degenerated d atomic orbitals, but after the electron splitting, we have a high-spin complex. So the reason we have this high-spin complex is because my crystal spacing is smaller than the electron pairing energy. So the 4th electron will go to the higher lying atomic orbitals. All right. So that's an example of a weak field configuration forming a high-spin complexes. And the justification here is for these weak field configuration, the crystal splitting energy is smaller than the electron pairing energy. It is high spin. When we have high spin, it means we have more unpaired electrons. So that's our first example. Second example, now we're similarly having manganese 3+, but instead of water, now we have cyanide as our ligand. So these cyan or cyanide, they're examples of strong field configuration. Use a different color. Or when we say strong field configuration, what we mean is this crystal splitting is larger than the electron pairing energy. And what we're getting is called a low spin configuration or low spin complex. So when we say it's a low spin complex, what it means is when we put the electrons, the 4 electrons, into that splitted atomic orbital, what we have is 1, 2, 3, 4. It is low spin because we have less number of unpaired electrons. And the reason we pair them up is because that crystal spacing energy is larger than the electron pairing energy. So the bottom line here is what my expectation to you. I will always tell you whether or not a ligand is a strong field ligand or a weak field ligand. But with that information, I might ask you to create these type of splitting diagram and assign electrons accordingly and derive information out of it. So I don't expect you to know if a ligand is strong field or weak field, but given that information, can you tell me something about that complex? Yes?
Sorry, how do you know whether to assign an electron to the higher energy?
So here, remember, we're always talking about the relative energy. When you put the electrons into the same atomic orbital, it is requiring an extra electron pairing energy. So depending on the relative difference between that electron pairing energy and the crystal splitting energy, you have different choices, right? So in the high spin complexes, this crystal splitting energy delta is smaller than electron pairing energy. So naturally, electrons want to go to that lower energy option, which is populating that higher lying dx squared minus y squared. Alternatively, in the low spin complexes or a strong field configuration, because my crystal splitting is higher than electron pairing energy. So now the electron would rather pair up instead of going that extra step to take that higher lying orbital. Yes?
So just as a reference, the top with the dx squared minus dxy dz is the crystal splitting energy orbital? Or
So the energy we're talking about, the crystal splitting energy, is the difference between these two states, right? So the top we have the dx squared minus y squared and dz squared. They are suffered by larger electron repulsion energy. And on the bottom you have dxy, dx, and dyz. So the difference between these two sets of atomic orbitals are my crystal splitting energy delta. Thank you. Okay, as a quick summary, these are the two complexes we talked about. Depending on what kind of ligand you have, on the left-hand side, we have a high spin configuration with small splitting energy, which is delta naught smaller than electron pairing. And that's because H2O is a weak field ligand. So these informations are correlated with each other. So for example, I can tell you water is a weak field ligand and ask you to derive if it's a high spin configuration. Or I can give you the electron configuration and ask you to tell me if that ligand is a strong field ligand or a weak field ligand. So they're correlated with each other. And I mean, we can ask it in one direction or the other way around. Just keep that in mind. On the right-hand side, you can have cyanide. So if we work it the other way around, as we start from cyanide being a strong field ligand, and what we can go back is that this complex has a low spin configuration. And we'll have large delta, which means delta is larger than electron pairing energy. Right, so it's like working in both directions. And just think about, I can give you part of this information, you can derive the other two. How are we doing so far? Yes?
Will we be given the electron pairing energy?
Well, I don't expect you to have a quantitative comparison. It's more like I tell you if it's big or small, that's bigger than electron pairing or smaller than electron pairing. Okay, so that's the octahedral field splitting or the octahedral splitting pattern. So again, everything we talked about here is called the octahedral splitting pattern. The reason dx squared minus y squared and dz squared are higher is because in the octahedral ligand field, these two atomic orbitals are directly interacting with the ligand. That's why they're higher. So that's only for the octahedral. For different molecular geometry and different number of ligands, you can have different splitting pattern. So just move on to see another example here. Square planar. Like what we said, square planar is also another typical molecular geometry for transition metal centers. In our last lecture, we mentioned that square planar complexes are commonly observed in late transition metals like palladium. They're nearly always four-coordinated square planar complexes. So we'll apply the same geometry in working out the crystal field splitting for square planar complexes. So here we go. Again, this is the ligand field. It's a hypothetical ligand field where just imagine my ligands are on x and y coordinates. And then let's just draw the atomic orbitals and try to derive which one of these atomic orbitals are highest in energy, which one of them is the lowest in energy. So, the x squared minus y squared. Here we still have the atomic orbital pointing directly to the ligand. So in this case, we have 4 direct interaction or overlap. And because we have 4 direct overlap, we're expecting the largest electron repulsion energy or highest energy. Alternatively, when we have dz squared, now the dz squared no longer have any direct interaction with the ligand. Rather, it has 4 indirect interaction. My dxy here is share the same plane, so it's likewise also have 4 indirect interaction. So these two will have slightly lower, but still relatively high orbital energy. It's just lower than the dx squared minus y squared. And when we move on to talk about the xz and the yz, the xz, that's like this. So it has some overlap, so indirect overlap with only 2 ligands. The dyz, that's the same idea. And we have 2 indirect overlap. Let me use a different color here. So that's why we're expecting the xz and the yz, they have smallest overlap with the ligand, and thus the lowest energy. The xy and the yz, the xz look similar, but they're not degenerated. These two are degenerated. So for the square planar splitting pattern, what we have is something like this, right? So the xz and the yz, they're the smallest, they're degenerating energy. The z squared and the xy are similar, but they're not degenerated. The x squared over y squared, that's the highest in energy. So for me, I expect you to know the x squared minus y squared is the highest. The xz and the yz are the lower ones. For the middle ones, they are in the middle, but I don't expect you to understand why they're not degenerated. But that's the crystal splitting pattern for the square planar geometry. So one of the typical questions I could be asking is, given the splitting pattern like this, can you tell me why the x squared minus y squared is higher in energy comparing to the xy? So just think about how to answer that question. All right, so that's the crystal splitting for the square planar geometry. The tetrahedral geometry is quite weird, so I'm not going to draw it for you. But for the tetrahedral geometry, it's pretty much flipped comparing to the octahedral geometry. What we have is dx squared minus y squared and dz squared are lower, and then xy, yz, and xz are higher. but I don't really expect you to know why that's the case, but that's just a given fact. All right, so as a quick summary, crystal field theory. We talk about two different topics. The first topic is the crystal field theory part, which means given the molecular geometry of a transition metal complex, you can have octahedral, square planar, or tetrahedral, you're gonna have different d orbital split. So that d orbital split comes from the electron repulsion energy between your d atomic orbital and the ligand. So we spent a lot of time talking about the octahedral example, sometime on the square planar geometry, and a little bit touched on the tetrahedral geometry. So that's the first step. Depending on the molecular geometry of your transition metal complexes, you have different splitting pattern. The second topic is we talk about the ligand field strength. So depending on the identity of the ligand with the same crystal field splitting pattern, that splitting between the higher lying d orbital and the lower lying d orbital might be different. So that crystal splitting energy, the delta, comes from the identity of the ligand. Again, for this class, I always make it clear whether it's a weak field ligand or a strong field ligand. So a weak field ligand gives you high spin complexes. A strong field ligand gives you low spin complexes. And you need to know what high spin and low spin means. So high spin complexes means your delta crystal splitting energy is smaller than electron pairing energy. And then the low spin complexes will have the delta, the crystal splitting, larger than the electron pairing energy. All right, so that's our first part of today's lecture. And now we're moving on to our second part, which is magnetism, color, and structure of transition metal complexes. So this part is more or less how to use our understanding in transition metal complexes in solving some real problems. So magnetism. Magnetism is quite straightforward. This one we talked about several times. Is if we have no unpaired electron, we say that complex is diamagnetic, or that's being repelled from a magnetic field. Or if a complex have unpaired electrons, we call them paramagnetic, and they will be attracted to a magnetic field. So these can be easily related to our high spin versus low spin complexes. So imagine if you have a D6 transition metal center with octahedral ligand field. If it's a high spin complexes, then it will be paramagnetic. If it's a low spin complexes, it will be diamagnetic. That depends on your ligand field strength. So I left a question here as an example. It's like, if I tell you a ligand is a strong field ligand or a weak field ligand, can you predict the magnetic property of these octahedral complexes? So that's the example we were talking about. So in both cases, my cobalt is a D6 configuration. And depending on how you draw that splitting, right? For example, for my low field complex, cobalt F6, 3-, it's a high spin complex because fluorine is a weak field ligand. So when we assign these D6 electrons in there, they all go singly occupied. Alternatively, you can imagine if you have a strong field ligand, like with cyanide, because the splitting is is a strong field ligand with a low spin configuration. So when you put the electrons in there, you have them paired up on the bottom 3 atomic orbitals. And these will have different magnetism. So on the left, this will be para. On the right, it will be diamagnetic. So I left it for workup in the annotated note. Then the next topic is talking about color of transition metal complexes. So when we say color of transition metal complexes, color is something that we describe, but the real property of color is absorption and reflection of light. Light, as we know, are electromagnetic radiation. So, while we're having to measure the color of a transition metal complex, typically in solution phase, what people use is the absorption spectrum. Like any absorption spectrum, you start from a light source. That light source with initial intensity passes through a sample cell. So that sample cell likely contains solution of your target. It can be some transition metal complexes, can be a sugar solution, whatever. And after the light passes through that sample cell, you can measure the intensity again. So by looking at the entire graph, at the point where that specific wavelength or frequency is being absorbed, you'll see a drop in the intensity of the light. So whenever you see the drop of intensity of the light, it means the light of that wavelength or that frequency is being absorbed by the sample. So the nature of the color is related to the absorption. So when a molecule absorbs a certain color, what we see is its complementary color. So here's a little wheel of color. Depending on the wavelength of our visible light, say if yellow light is being absorbed, what we will see is purple light. And if green light is being absorbed, what we'll see will be a red light. All right. So to use this knowledge, what we can do is try to derive information about a transition metal complexes. Just know its color, or try to understand the color of transition metal complexes in solution phase. So let's work on an example together. Chromium hexawater with 3+. So this is a nice purple solution. It's pretty poisonous, so don't drink it. But why is it purple? That's the question we're trying to understand. So by using the crystal field theory, the ligand field theory, we can actually derive numbers that's supporting this color being a purple color. So if we draw out the structure of this transition metal complex, we can see it is an octahedral complex. Again, it is octahedral because it's 6 coordinated. We expect it to be octahedral. And water, we already talked about before, is a L-type ligand and also a weak field ligand. And this entire molecule has 3+. So knowing that, when we look at the chromium 3+, we can write out its electron configuration. Chromium 3+, that's D3. Or its d electron count is 3. So we write out its crystal splitting pattern. On the bottom, we have the XY, the YZ, the XZ, and on the top, we have the x squared minus y squared and dz squared. So when we put the electrons in, they're all singly occupied. And then the next topic will slightly relate to spectroscopy, which is our next lecture, but I want to quickly mention it. So that's the electron configuration of the ground state chromium complex. So that's the ground state. And let's remove the electrons. On the left-hand side, this is our ground state. And imagine now the sample is absorbing a photon and getting into its excited state. When say it's getting into its excited state, one of the electrons in the bottom will be promoted onto the top atomic orbital. And in this process, the energy required to promote that electron from the bottom to the top equals to our crystal splitting energy. Or in another way, in this specific example, the H mu will equal to our crystal splitting energy. Right, so we need at least that number of frequency in order to excite the electron from the bottom atomic orbitals to the top atomic orbitals. So experimentally, the crystal splitting energy can be calculated, and I'll give you that energy. For example, in this case, we can have the crystal splitting energy equals to 17500 wave number, and one wave number is equivalent to, say, frequency equals to 30 times 10 to the 9 hertz. So wave number, the cm here, that's a unit for our energy in spectroscopy. And then it becomes quite straightforward. We can plug in the number and solve for the wavelength that's being absorbed. So lambda equals to, this is C divided by mu. And we know that in this case, the wave number is already given. We already know the crystal splitting energy in wave number. So what we have here, you can solve for the wavelength that's being absorbed. I'll skip the calculation here, it's in your annotated notes. That's about 571.4 nanometer. So if we copy this 571.4 back to the wheel of color, we see the yellow light is being absorbed. So that is why this chromium solution appears to be a purple solution. We'll go into more detail about how to use the wave number and how to solve these spectroscopy problems in our following 2 lectures. So as a quick summary, what we have today is basically the spectrochemical series. So you have different splitting pattern, you have different crystal splitting energy, and these crystal splitting energy corresponds to the wavelength that's being absorbed in a given wavelength range. And that is why your transition metal complexes have so many different colors. And remember, depending on what color is being absorbed, we see its complementary color. So if a yellow light is being absorbed, we see its complementary color, which is a purple color. So that's ends for today. I'll stay a little bit for questions.